What we have been looking at the past several lessons are called Machin-Like formulas, named after the English mathematician John Machin. They involve a number of inverse tangents added together. Each term is multiplied by some coefficient c. The argument is some fraction a over b. When added together, these equal pi, or some multiple thereof, most often pi over 4. As we've seen through many examples, we can use the series expansion for inverse tangent. That means we can get an estimate for pi using only addition, subtraction, multiplication, and division. That is quite incredible considering the fact that pi is not a rational number. That is, it's not a fraction. It has a decimal representation that never repeats and never terminates. Of course, the catch is that we have to perform an infinite number of arithmetic operations to equal pi, so we never get there in the end. Nevertheless, we can obtain many digits. Some people have pushed these infinite series to get millions of digits past the decimal. That requires quite advanced computational equipment to achieve, and most ordinary people lack access to that. So it is, I content myself with the 15 digits that my software handles. If you wish to chase more digits, I leave that to you. Back to Machin-Like formulas. These are 4 examples of two-term formulas. We've seen how all these perform in a previous lesson. All these happen to have 1 in the numerator of the argument, but this need not be a restriction. If you allow any fraction in the argument of inverse tangent, an infinite number of these formulas exist. We don't need to restrict ourselves to 2 terms either. We have already seen the 3-term formula in the first line. Below it I have shown a couple 4-term formulas. You can keep going with 5 or 6 or even more terms. However many terms you want, really. The most efficient currently known Machin-Like formulas have multiple terms. Although I have omitted them from this lesson, the curious viewer can easily research them to learn more. I have restricted our conversation to simple Machin-Like formulas for the ease of demonstration, but the same principles apply to more complicated ones. With an infinite number of possibilities, that means someone could still discover an even better Machin-Like formula to find digits of pi. As far as I can tell, this is done by trial and error. Guess a combination of coefficients c and arguments a over b. Then check your answer, using complex numbers, Euler's formula, and scientific notation to simplify things. To beat the current record, these numbers are going to get quite unwieldy, especially considering you'll probably need at least 5 or 6 terms. That means your software will probably need to handle more than 15 digits in order to beat round-off error. It's an ambitious task that I myself have declined. If you wish to pursue it yourself, I wish you all the best. Alright, let's see an example that involves crunching some numbers. This will look very similar to the first lesson of this subseries, except I'm going to use the 3-term Machin-Like formula seen at the top of the page. I've used color coordination to help you see what's going on. Though I didn't explicitly write it here, please be aware that every other row in the 3rd, 4th, and 5th columns is negative. The sum of an individual row, boxed in purple, is equal to the sum of the numbers in the red, blue, and green boxes. For each row, the number boxed in purple is equal to the sum of numbers boxed in orange, up to that row. Since the sum is equal to pi over 4, we must multiply by 4 to get pi. Look in the 3rd, 4th, and 5th columns to see how quickly these numbers tend to 0. That is indicative of rapid convergence. Of course, we get this good performance because 1 over 18, 1 over 57, and 1 over 239 are small fractions. The smaller the better. Graphically, I have plotted the number of digits per term. We max out at 15 digits after only 6 rows. That is why the graph flattens out. This is certainly the best performance we have seen thus far. In general, It seems like the more terms we have in our Machin-Like formula, the better the performance. There could be a trade-off after a certain number of terms, but I haven't explored many Machin-Like formulas beyond 3 terms. If you wish to explore this question yourself, please let us know in the comments section what you discover. Also feel free to ask questions. If you enjoyed this video, please consider sharing it with a friend you think could also benefit. I appreciate your support and look forward to seeing you again.